Hello, this is a presentation for the Kansas State University 2015 ASHRAE Student Design Competition System Selection. To begin, let's look at a brief overview of this presentation's topics. First, the design team will be introduced and the building identified. Next, owner's requirements, design team's goals, and ASHRAE standards will be identified as project goals. Then, an HVAC system will be selected and its components will be identified. Further, the system's overall performance will be analyzed by the team. And finally, the design team will make their recommendations for this building's HVAC system. The members of the design team include Jordan Crook, Ryan Mirso, Joshua Padley, and Grant Faulkner. The advisors to the design team are Julia Keene and Fred Hassler. The proposed building is a new 3-story, 46,400 square foot junior college in Doha, Qatar. The building's occupants will include students and administrators in 3 key space types: classroom, library, and IT spaces, office and administration spaces, and special instruction spaces. The climate of Doha is extreme because it is located within a desert and is adjacent to the Persian Gulf. Per owner's requirements, 2% cooling design and 99% heating design were used to determine that the design summer temperatures are 106 degrees Fahrenheit dry bulb and 73 degrees Fahrenheit mean coincident wet bulb, and the design winter temperature for the location is 57 degrees Fahrenheit dry bulb, and the location near the Persian Gulf generates high humidity conditions, which equates to a 77% relative humidity. TRACE 700 software is used to calculate the total heat gain and heat loss of the building. The peak heat gain is 171 tons and can be broken down by source to show that the majority of the cooling load is due to the occupants and ventilation requirements. The peak heat loss is 420 MBH. In early stages of system selection, the design team established 7 goals based on the owner's requirements and ASHRAE standards for the selected HVAC system. Those included good economics, great indoor environmental quality, low environmental impact, architectural synergy, acoustics, control, and ease of service. Using these goals, the team was able to develop an initial performance matrix to help select the 3 different systems to be analyzed for this building: air handling units with VAV boxes, packaged rooftop units with VAV boxes, fan coil units, chilled beams, VRF, underfloor air distribution, and ocean loop heat pumps are the 7 systems that were included in the initial performance matrix. The design team analyzed each system's performance based on the goals previously established to narrow the list of systems. The X's signify a system that is determined to perform poorly in the category, and the check marks signify a system that has performed well in the category. Based on their exceptional performance across the board, chilled beams and ocean loop heat pumps were selected to be the alternatives analyzed further. In an effort to compare direct expansion to chilled water, the design team expanded the chilled beam system to one with chilled water dedicated outside air system and one with direct expansion dedicated outside air system. Therefore, the 3 alternatives selected for further analysis are: Alternative 1, ocean loop heat pump; Alternative 2, chilled beams with chilled water DOAS; Alternative 3, chilled beams with DX DOAS. The design team then created a new matrix to evaluate each alternative's economics, comfort and health, environmental impact, adaptability, serviceability, and synergy with architecture. These categories are chosen to reflect not only the design team's goals, but also the owner's requirements and ASHRAE standards. Each alternative was evaluated via comparison matrix, and the point totals shown were calculated. Alternative 2 achieved the highest score, receiving 79 points. Because it achieved the highest matrix score, Alternative 2, chilled beams with chilled water DOAS, was selected as the best HVAC system for this building. The complete system for Alternative 2 is now shown. Let's go deeper into this system to discuss how each component will work to produce ventilation, cooling, heating, controls, and pressurization for this building. To reduce the amount of mechanical cooling required for conditioning ventilation air, an earth tube system will be used. This system works by drawing outside air through ducts below grade. This process will lower the temperature of the ventilation air in the cooling season, reducing the required capacity of the DOAS air handling unit. The ventilation air will then be conditioned by air handling units designed to handle only outside air. This dedicated outside air unit will provide outside air to the space in order to meet the code-required ventilation airflows, as well as providing humidity control for the space. The outside air will need to be dehumidified before it enters the building. Dehumidification requires a low leaving air temperature, and in order to prevent uncomfortably cold air from entering the space, the air will need to be reheated. A horseshoe heat pipe will be placed around the chilled water coil inside the air handling unit to lower the required heating and cooling. First, the hot, humid air passes over the cool refrigerant, which removes the heat from the outside air prior to the cooling coil. After the air passes over the cooling coil, which overcools the air to achieve the desired dehumidification, it passes over the hot refrigerant, heating the air up to the desired temperature to be supplied to the room. The addition of heat to the refrigerant causes it to flow around the cooling coil due to the difference in temperature inside the horseshoe. According to ASHRAE Standard 62.1, Section 6.2, MERV 11 filters at a minimum must be used to clean the outside air. To provide the needed filtration, bipolar ionization tubes and inertial air filters will be used. Inertial filters will remove the sand and other large particles from the polluted air by passing through a series of U-turns, causing the harmful particles to separate from the air and fall into a collection bin. After the inertial filters, the bipolar ionization tubes will use electrodes to charge the harmful particles, attracting them to oppositely charged plates, removing them from the airstream. Active chill beams will be used everywhere other than the workshop areas. This is because of the dust that could clog and decrease the performance of the chill beams. Active chill beams condition the space by passing dry air from the dedicated outside air unit over a chilled water coil. This air then drops into the space. Chilled beams take advantage of warm air rising in the space through induction to pass back over the coil, to be cooled and drop back into the space. Fan coil units will be used in the shop space rather than chilled beams because they contain a filter, allowing them to remove airborne particles from the saws, metalworking equipment, and paint booth. They are also selected because chilled beams are not as effective in spaces with tall ceilings such as special instruction spaces. These units will use chilled and hot water coils to condition the space. The chilled water for the chilled beams and FCUs will be created by a combination of chillers to increase the efficiency of the system. The hour cooling output of the air-cooled glycol chiller is shown in light blue below. A glycol chiller will operate at night to charge ice storage tanks because the utility rates are lower and the nighttime dew point is lower, allowing the chiller to operate more efficiently than during the heat of the day. An air-cooled chiller, whose output is represented by the green bars, will be used to create chilled water at night while there is no available solar energy to power the absorption chiller. During the daytime, this chiller will act as a backup chiller for the absorption chiller to ensure that the building's cooling system can still operate if the absorption chiller fails. Both chillers will be located on the roof of the building. Because the building is charged at a higher peak electrical utility rate during the day, an ice storage system will be used to reduce energy costs. The ice storage hourly output is shown below in dark blue. This system utilizes the glycol chiller to create ice at night when utility rates are low, and discharges this cooling energy during the day when utility rates are at their peak. This concept is called peak shaving. The ice storage will assist the absorption chiller in meeting the daytime cooling load. The ice that is created is stored in large tanks below the building. When the cooling need exceeds the capacity of the absorption chiller, water flows through these storage tanks, cooling the water. An absorption chiller, whose output is shown below in yellow, will be used to produce chilled water during the daytime hours. This chiller type was chosen because it can use hot water as an energy source. By coupling the absorption chiller with a solar collection system, chilled water will be created using energy from the sun. Cutter averages 9.5 hours of sunlight per day. The design team sees this sunlight as an energy opportunity, not a burden. This energy will be harvested by way of parabolic solar troughs placed on the roof and will be used to heat water for the absorption chiller. These troughs will track the sun as it travels across the sky and uses mirrors to concentrate the solar energy on a pipe filled with thermal heating oil. This heated liquid will then flow into a heat exchanger, where it will heat up water for the absorption chiller. To ensure that the building can overcome an unexpected sandstorm, this system will have a 15-minute backup tank to give the air-cooled chiller time to start up. Other than providing hot water for the absorption chiller, the solar collection system will provide hot water for the chilled beams and fan coil units. A condensing boiler will be redundant to the hot water created by the solar collection system to ensure that the building will always have heating. To ensure occupant comfort, a high level of control capability is pursued throughout the selection of the HVAC system. To give the occupant thermal control of their space, each space is given its own zone, and larger external spaces are divided into multiple zones to ensure that the space will be properly conditioned. Humidistats, thermostats, CO2 sensors, and air pollutant monitors will be located throughout the building to ensure human comfort and will communicate with the building management system. The exhausted spaces in the building include restrooms, grounds room, mechanical spaces, and the special instruction space. The special instruction space is divided into three main purposes: carpentry and woodworking, welding, and painting, each having their own dedicated exhaust system. In total, the special instruction space will be exhausting 14,970 CFM. To evaluate pressurization, the building is split into two parts: the main 3-story building and the special instruction space. Ventilation air will be supplied to the main building, then is distributed through transfer ducts to the special instruction space. It is imperative that this space is to maintain slightly negative pressure in respect to the main building to ensure that no fumes or dust particles are drawn back into the main building through the transfer ducts. Because the building is required to bring in more air than it must exhaust, 2,545 CFM of relief air is removed from the building to maintain desired pressurization. When the paint booth exhaust system is on, a dedicated makeup air unit located on the roof will supply the space to maintain pressurization. To analyze the cost effectiveness of each alternative, a 50-year differential life cycle cost analysis was conducted. A life cycle cost not only includes the first cost of equipment, but also operating costs. Operating costs include the costs to maintain and operate the systems. Alternative 2 has similar first costs to the other two alternatives, but when combined with the operating costs, it emerges as the most effective option. The system performance describes the advantages and disadvantages of the selected system with respect to economics, sustainability, adaptability, serviceability, environmental impact, and architectural synergy. Alternative 2 provides superior economics because it is determined to have the lowest 50-year life cycle cost of all three alternatives. The ASHRAE Green Guide defines sustainability as providing for the needs of the present without detracting from the ability to fulfill the needs of the future. Alternative 2 provides for the needs of the building while also providing the lowest carbon footprint in comparison with the other alternatives. Adaptability is the system's compatibility to accommodate load changes and future building expansions. The active chilled beams selected for Alternative 2 can easily accommodate load changes because of their ability to modulate the volume of water flowing through the chilled beams. Accommodating for future expansions will be difficult for Alternative 2 because the central cooling plant is sized off the current loads, and additional equipment and piping will be needed to meet the added load. Serviceability of the system is based on the ease and regularity of maintenance. Since chilled beams have few moving parts, they require little service and most equipment is centrally located, making Alternative 2 easy to maintain and very reliable. Environmental impact deals with the system's energy use. Alternative 2 has the lowest energy use of all three alternatives and uses over 60% less energy than the ASHRAE 90.1 baseline system. Architectural synergy is the system's ability to fit in the given mechanical space and enhance the aesthetics of the building. Chilled beams require little plenum space. Chilled beams also add to the aesthetics of the space. The Kansas State ASHRAE student design team recommends Alternative 2 chilled beams with chilled water DOAS because of the superior economics, sustainability, adaptability, serviceability, environmental impact, and architectural synergy. Thank you for your time.